An amplifier composed of two common source stages is given. The key component values are annotated. The arrow of the source terminal of M1 is not shown on purpose. You need to figure out where it is yourself. So it is here. The explanation why it is here you can find in my previous videos. Vsig, so this is the signal voltage, is the input signal voltage source, and Rsig, so this one, is the output resistance. Using the Miller approximation, find the approximate frequency of the pole formed at the amplifier input. So we want to understand what is the pole associated with this node. An important thing which is said here is using Miller approximation. So avoid deriving equivalent circuits and calculating the input impedance with a test source Vx, looking at the Ix, calculating Zx. Avoid this because you will deviate from the result, not significantly, but you will not get exactly one of these results. So this is also why here in the question it said which of the given choices is the closest to your estimation. So if you use Miller approximation, you get very accurate approximation, very accurate. You'll be very close to this one of these options. But if you use exact calculation, which is that you make the equivalent small signal diagram of the input stage M1 and then work out the input impedance with the test voltage source, you a little bit deviate from this, but you will be still very close. Why is that? You can find back in the lectures, but it has to do with the fact that the output impedance of the first gain stage for M1 is not zero. So Miller theorem and Miller approximation assumes that the output impedance of the amplifying stage is zero. This is not the case. This is real transistors, so it's not zero. So there will be a term which will shift the approximation of actually the equivalent capacitance C gate drain. But we'll see. You can try using equivalent circuit. You'll get a very close result. So now let's get the shortcut, which is indicated also in the question, through Miller approximation. Now the pole, at every node we can associate certain time constant, and the time constant will be equal to the equivalent resistance of the node times the equivalent capacitance at the node. So now this is the equivalent resistance because there is no other, and the equivalent capacitance we have to compose it. So we will have something like R equivalent and C equivalent. This thing here is simple. This is 100 ohm. There is no other resistance because the resistance in the gate is infinite. So it will be 100 ohm, just the input resistance. And now the question is reduced to finding what is the equivalent capacitance. So the equivalent capacitance will be composed by the capacitances that are connected at this node. And we have basically two capacitances. One will be C gate source, and the other will be C gate drain. Now the problem with C gate drain is that this is a Miller capacitance. So this means that its value, effective value, or the charges needed to charge this capacitance, depend very much on the gain of the first stage. So now for the equivalent capacitor I can write C gate source plus C gate drain multiplied by the Miller effect, 1 plus the gain of the stage, where A is the DC gain of the first stage, which for common source stage will be GM1 R out 1. Now let's see what I'll get. So C equivalent is C gate source is simply given 20 femtofarad plus C gate drain is 5 femtofarad, but now I'll have to multiply it by the gain of the first stage, GM1R out. Why is that? Because if you have a signal here, you will invert it here and amplify it. So the effective change across the terminals of the capacitor is much more than your input signal. Hence, the effective capacitance that you see is multiplied. And this is the Miller effect. This gate drain capacitance is the Miller capacitance. And the effective value that we see at the gate is multiplied. In other words, if you want to represent this gate drain capacitor as a capacitor equivalent to ground, you have to take its nominal value and multiply it by 1 plus the gain. So the gain is 1, and now for the GM here of this transistor, we can use V over drive and the drain current. So it will be 2 times the drain current divided by V over drive. Now for air out, I'll use the early voltage, which is VA, divided by the current, by the drain current, I drain. So this will cancel and will make our life a little bit easier. So we will have 20 femtofarad plus 5 femtofarad. Then I'll have here 1 plus 2 times VA is 10 volts divided by V over drive is 0.2. So this is 1 and this is 100, and then this is 101. So C equivalent, now we get for C equivalent to be so this is 505 plus 20, 525 femtofarad. Now we can calculate tau is 100 times 525 femtofarad, and this is ohm, which means for the input frequency, for the input pole frequency, we get 1 divided by 100, 525 10 to the power of 15, or we have 10 to the power of 6, 100, 525 times 10 to the power of 9. So let's calculate this. We have 1 million divided by 100 divided by 525. This will be 9.04. So we in is 19 10 to the power of 9, and then radians per second. Hence the good answer is this one. This is the good answer. Thank you very much.